Okay, and we'll start up in a couple seconds. Any questions before we begin? Okay, let's begin. I think we were right in the middle of this last time. So we were discussing this code and just kind of seeing how the Bootstrap works. But the Bootstrap, it's really trying to replicate this process of going out into the population and recollecting new samples. And so we were right in the middle of comparing the Bootstrap to that. So instead of going out into the population over and over and over again and grabbing n samples, computing a test statistic, and looking at its empirical distribution, which I always say, if I could do anything as a statistician, that's what I would like to do. And it's more of a conceptual statement, because anybody could do that, just tell somebody to go out and get more data, but that's at least what we're understanding. We're trying to understand the variability in that statistic. And so I will say this, Bootstrap doesn't give you a better estimator. And we'll see this next time. What it does is it quantifies the uncertainty around that estimator. And so I think we'll see that pretty soon. So it doesn't give you a better point estimator, it quantifies uncertainty, and a lot of people have a hard time with that. You know, like, why do you want to do that? It's so you can understand what's random from what you're studying. So there's random variation from sampling altogether. If we had all the information out there, if we had every data point out there, we don't have uncertainties. We don't need to do stats. But going out there and getting all of the data is prohibitive. So you can't go out there and do it. So it's going to cost you too much time and too much money. Ergo, there's statistics. So the Bootstrap is our savior in this case, where we can't go back out into the population, but what we can do is we can go back out into our sample that we already have and resample that. And all we're getting out of that is an understanding of the variability in that sample. Now, if the variability in that sample is not representative of the variability in the population, the Bootstrap will not work. So you don't have a good enough understanding of what the distribution of the data is out in the population. But I will say this, unless you knew a lot of stuff and you could mathematically model all that, the gaps in the distribution that you're not observing with your sample, no technique will work. And so, another question is, how do you know you have enough data that it's representative of the population? And unless you're willing to go out there and every once in a while check other data sets or look at holdout data sets or something like that and see if your data is able to predict stuff that you're not fitting your model to, you'll never know. And so it's one of those impossible missions. How do you know you have enough? Hopefully you're able to forecast or something like that. Cross-validation is kind of a pseudo way of trying to forecast. So if your stuff isn't forecasting, whatnot, then you don't know. What I like to do is I like to always build up simulation studies and say in a problem like this, and I try to always build a forward simulator of what the data looks like from a particular process. So I try to model that process, and then I run a simulation study up front, and I say from a process that I'm assuming, or at least I'm going to validate later on, is representative of the data that I'm observing, and I get some finite data set out of it. I look to see how reliable it is in estimating all the functions I need to estimate, all the parameters I need to estimate, so on and so forth. And so I always do a simulation study up front, just to study that, make sure I have the right asymptotics. In reality, you never really know. All you can do is just go back and try to validate. Okay, so the Bootstrap, pretty easy conceptual idea, sampling with replacement from your sample. A sample from a sample is a sample. Okay, so all we have to do is just sample uniformly from our sample, and ultimately we're sampling from our underlying distribution. So we were studying this problem, where I ended up making a mixture model, where I have 3 different normals, and I'm going to mix over them in an additive fashion. And we'll be studying mixture models later on in this class. So stuff that's not in the book. But mixture models can look like this, and there's a lot of different types of mixture models. I don't know if this is exactly what I drew, but we're going to be seeing data from this distribution. All I'm doing is I'm just grabbing 3 different normals with weights. So this is probably a lot smaller because my weight associated with it is 1/6. This is supposed to be the big mode. This is the medium mode. So flip this around and get right. We'll draw the picture in a second. I'm going to keep going back out into the population, sampling data sets. And then I'm going to compute some test statistic. We're inclined to start with looking at X bar. So saying that, you should never really do this. And so X bar, we already know the distribution of it, so long as there's finite variance. And we'll be studying the central limit theorem next week. So that's coming up as well. But if you didn't know that, you could run the Bootstrap and your mathematical limitations won't limit your inferences. So let's just have a look at this. What we're going to do is we're going to, just as a reminder, sample R times, capital R times, going back out into the population and resampling from this distribution. We're going to do that N times. Compute our test statistic, and I'm going to repeat that process cap R times, cap R for replicate. Then I'm going to take my very last sample. So I'm just going to grab a sample at pseudo-random. I'm just going to grab my last sample that I ran out of the population, and I'm going to bootstrap over that sample. And I'm going to do cap B bootstrap iterations. And that's down here. I haven't shared this code with you. The range, mid-range example that I was piquing your interest with, that one's on the website. So you can download that. You're going to code this up yourself. So it's not difficult. So the bootstrap is 2 lines of code. Random sample. The true says with replacement. If I put false, then I would have to say how many samples I would like without replacement. I can add weights to this, so on and so forth. And then I just compute my bootstrap statistic. So we're studying the mean to start with. We can change that statistic. I already preempted that maybe we want to study the variation or something like that, or some other function of the data. Now what we're going to do is we're going to compare those to each other. So those 2 different distributions. So let's do it. Just as a reminder, for this we've got R is 500, cap B is 500, the number of bootstrap replicates and the number of replicates going out into the population don't need to be the same. So, but let's just use this as a starting point and play around with this a couple times. I picked N is equal to 31 just to be facetious. I've seen this written so many times in undergraduate textbooks that say, well, just so that you make sure you have N is equal to 30, which is the rough rule of thumb for a good sample, we'll make it 31, so we can safeguard that. It really is just wounding every time I see that. So that's not true. That's such a rough rule of thumb that we should probably just get rid of it. So these things we tell undergraduates and then we expect them to forget it in graduate school is probably not the right way to go about business. Nowadays, we can simulate everything and see how stuff operates compared to our theory, and I think that's what we should do. Okay, and that's what we're going to do. So boot example, I'm going to go out into the population and sample this 500 times, and that's what you see flashing on the screen. So each one of our samples is just one of those, and you can kind of see the 3 modes filling out. I did say last time the number of bootstrap samples is 2n minus 1 choose n. And I heard some other answer like n to the n or something like that. And that's probably looking at the probability of a sample is where that confusion arises. I hear that answer a lot and I can understand it. So for each element there's n possibilities. So I have a probability of 1 over n of grabbing any of them. And I've got n of those, and I'm going to product that together. So I'm going to get 1 over n raised to the n, and that's the probability of a particular, sample. And you might be thinking that this is the total number of unique bootstrap samples. And so let me just show you why this is true. I had a couple questions about this from last time. I guess my explanation wasn't very good. So let's just say n, we'll come back to the code and look at it in a second. N is equal to, let's say, 5. Okay, here's the argument. Here's the combinatorial argument for this, right here. I'm going to come up with the right picture to explain everything. So I guess if I take this back to my math instructor, he'll probably say, that's not good enough. So I don't like your picture. I want you to come up with a lot of mathematical notation. And we can come up with mathematical notation for this. But I think that the picture actually is probably the best version of this proof. So we'll stick with that. So I'm just going to write down 5 items. They're all unique. I'm going to call them stars. So 1, 2, 3, 4, 5. Okay, and they're going to represent my n objects that I'm going to grab. I don't know which ones I'm going to grab, but I'm going to introduce this partitioning notation for everything. And I'm going to introduce n minus 1 partitions. And that's all I need to be able to separate all of this out. So I've got 1, 2, 3, 4, which is n minus 1 different partitions. So let me just give you a couple examples of what this might mean. This right here would mean that you've seen every sample. So this is my first sample right here. This is in the first location. This is in the second location. This is the third location, fourth, fifth. So this is like getting x1, x2, x3, x4, x5. So that's our original data set. So I'll just write cap x is x1 to x5. Okay, so this is just an example what this means. Let's do another one. So I've got my 5 stars. When I learned this, and I've never forgotten this terminology, people call this like the stars and bars sort of notation for coming up with partition. Is that familiar to you guys? You guys hear that in probability class or anything? Okay.
Like balls and walls.
Yeah, lines and balls, whatever. So, yeah, okay. So I call it stars and bars. Did yours run?
What's that?
Did your thing run? No, this is better. Okay, let's just do another one. So I'm going to do 1, 2, 3, 4 of those. So what I mean with this is I've seen in the first position x1 twice. So this means x1, x1. There's no x2s in there. That's empty. We've got an x3, x4, x5. One more just to make sure we've got this. So this is our sample, our bootstrap replicate would be this. So star, 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 star. So let's just do 1, 2, 3, 4. So what does this mean? This is going to be x1, x1. There's an x2 in there. There's an x3. There's no x4s, and there's an x5. So I can define every bootstrap replicate with this notation. So there's no x4 right there. So every bootstrap replication. One more. So let's just say this is 1, 2, 3, 4 right there. That's a possibility as well. And so what does this mean? So I've got the x1. I don't see any of these x2, x3, x4. But I do see a bunch of x5s. So that's our notation. So I've got x1, x5, 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 x5. So lots of different things that we distinguish with this notation. Question is how many different rearrangements can we observe of all of this? So I've got these n indistinguishable stars, so there's n things. I have n minus 1 indistinguishable bars, so there's 2n minus 1 things. I could either choose the n minus 1 or the n, it's exactly the same. So if you work this out. So this is 2n minus 1 factorial over n factorial, n minus 1 factorial. That's a big number. So let me just ask a question. If n was equal to 10, how big is this number? Approximately. What do you think? Bigger than 2,000? Yeah, way bigger. So, like, much, much bigger. So let's just kind of look real quick. So, n choose, I did this morning just to look at it. 10 times 2 minus 1 choose 10. It's like 92,000. So even with a very small sample size, and I probably wouldn't recommend doing too many analyses with like 3 data points, we could see how well it worked. Probably not too well, and that won't be any great surprise to you.
I have a question. If we have outlier in our data sets,
If we have what?
outlier
Okay.
in the sample data set,
How do you know it's an outlier? What does that mean to you?
we have sample, but it's very rare in general,
Yeah, so what is an outlier to you?
maybe by previous knowledge.
Yeah, maybe. So it's hard to know what outlier means. So that's kind of comes with model in hand. So if I knew everything was supposed to be normally distributed and something didn't fit the trend, then I might call it an outlier and I might be inclined to throw that thing away. But if I have real Cauchy data, if I were studying the stock market, I saw these crashes every once in a while, but everything was kind of like stationary for a while, and all of a sudden, well, bam! I don't think you could go to your financial advisors. Eric's worked at the Fed. Could you just go in there and say, well, I just want to throw that away? So, no, that's the important thing. And so you might think that that's outlined, but I don't like that definition. I would want to distinguish whether or not it was a real thing or something you throw away. So if it were real, and you really believe it, you should leave it in there. So yeah, I wouldn't toss it. I would inspect very carefully anything that deviates from the rest of the pattern. So I think they like to teach people so that you can assume normality is toss all your outliers, look at Cook's distance or something like that, the Mahalanobis distance, throw things away so that you can fit some fictitious model. I never do that. I always heavily investigate whatever the deviating pattern is. But for the bootstrap.
Yeah, and one of our samples, for example, X1 is outlier. In one of our samples, we have 5 X1. And it's exaggerate the outlierness in our data set.
I don't think so. I think it's for your data. If you believe it's really there, then it should be there. But how often are you going to have X1, 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 X1? Not very often. And so I think it's actually handling that case properly. So if you believe it's something real. And so I would be inclined to leave it in there. Yeah, so I don't think it exaggerates. So it exaggerates that just as much as it exaggerates any other observation in the data set. So we're sampling uniformly from it. So I don't think we're placing any extra weight on that compared to everything else. Question in the back?
Yes, Dr. Lehman, my problem is with proof. How are we choosing n out of the 2n minus 1 stuff that we've got?
How am I choosing n?
Yeah, I don't get the...
I see. So this, I could choose n minus 1 as well. This is 2n minus 1, choose n minus 1. Those are the same. So what I'm choosing is either, so what we're doing in this thing is I'm looking at the total number of rearrangements. So permuting this whole thing, how many permutations are there? 2n minus 1 factorial. I can scramble this up. But I can interchange the stars without changing anything. So I can flip those around. How many stars do I have that I can reshuffle around? And it's exactly the same thing and you can't distinguish it. I've got n factorial of those. How many bars can I rearrange? Same argument. And make everything indistinguishable because they're not labeled. There's n minus 1 of those. So I can shuffle those around. So how many possible indistinguishable orders are there of this? It's this number right here. So again, the argument is how many total permutations are there? This is a multiplicative thing that we're looking at, but we want to get rid of indistinguishable permutations. That's why we're dividing out the n factorial permutations of the stars and minus 1 factorial permutations of the bars.
Okay.
Does that make sense?
Yeah, thank you.
I hate explaining combinatorics. So, anyway, chew on that for a while. Okay, so even with relatively small samples, there's a lot of Bootstrap iterations. There is a paper out there that's called How Many Bootstrap Iterations Are Necessary? And it starts off and it says, usually 1,000's not enough. So you really want to make these things really big. So tens of thousands, hundreds of thousands. So I don't know if we need all 92,000 of these, and because I'm doing this in class, I want it to run a little bit faster for us. You know, but I would be thinking something like that. 50,000 iterations would probably be pretty good. So, but I'm not going to enumerate all 92,000 of the things because it's more computational effort to do that than just throwing darts and grabbing things at random. I think this is one of the big surprises of the early 1900s, that it's hard to keep throwing darts. And so just doing things at random, you could try to come up with some design and figure out which one of these you need, but it would cost you more effort and it would make the coding harder. So I think people like this because you can just grab them at random, but crank that number up. So I would say compute this number and try to compute something on the order of that. But ultimately the answer is what I do is I bootstrap replicate and I look at that distribution that we formed. So we formed some distribution. Let's look at these. Here's our two different distributions. So the one on the left is from the population, and the one on the right is my bootstrap replicate. So what I would be doing in practice is I'd be staring at this distribution right here as I crank up the number of bootstrap iterations, and I'd wait for this thing to converge. Anything that I wanted to say about it, whether or not it was the mean that I was looking at, somewhere around here, I'd be computing the mean. And if that mean was changing as I was cranking up the number of samples, well then I would keep cranking it up until all of a sudden the mean didn't change. What people are worried about is in the tails, making sure you've got the right tail behavior. And so I'd probably also be computing intervals or something like that. Probabilities over to the 2.5%. If I were going to compute like a 95% interval, I'd be paying close attention to those 2.5% quantiles. 2.5% on the left, 97%, 97.5% on the right. So anything I wanted to compute, I'd make sure that's converged. And that's going to be my answer to everything. It's called Cauchy convergence when you study that. So basically look at the last couple iterations in your sequence, compute that thing and make sure they're close to each other. And compute it until they're close to each other. So that's the real answer. So you could write a whole paper on it and get 92,000 citations if you wanted to. Somebody's already done it though. So, and essentially they see that. So it's nice to write a paper like that because sometimes, every time you do a bootstrap analysis in your real research, people are going to go, how do you know you've done enough iterations? So if you cite something and you say you did it, that's the magic wand in academia. Okay, so all pretty easy principles. You don't need to be a mathematician to figure this out. Where we left off last time is asking the question, are these distributions the same? So this is the distribution associated with going back out to the population, and the right thing is trying to mimic that. And just going back into our sample and resampling, they're clearly different. So, but how close are they? So I asked you last time is to look at QQ plots. And that's what this is right here. So just to get an idea of what this thing is, what we do is we look at some quantile. I'm just going to do this fictitiously and give you a coarse impression of this. It's probably looking at the 1/500 quantile since there's 500 samples and everything. But I'm just going to say this a little bit more coarsely. So let's say this is 5% of your data. So imagine I had 100 data points. There's actually 500 in here. So, but if I had 100 data points in here, I would order them. And then I would look at the 5th observation, and I would look at where the 5th ordering happened, and that would be the 5% quantile. I do that for this distribution, and I do that for this distribution. And I look at their quantile values. So 5% of the data is to the left of that, 5% is to the left of that value. They're slightly different values. I plot that over here. Then I'd march over, maybe go to the 10% quantile, see where that lies. Have to order all of my data to do it. Do the same thing over here, and then plot those right next to each other. And so you can convince yourself that this will be a straight line if those distributions are the same up to scale and location. And so the scale of the distribution will change the slope. So if the scale is going to be the same, the slope is going to be approximately 1. And the shift is the location, or the intercept is the location in all of this. So they're not exactly the same. So mostly you're just looking for the linear pattern right here. So if I looked at this, I got a lot of insight out of it. This is why I really like QQ plots. So if it's a one-dimensional thing, and somebody says to me, well, I computed a test statistic, whether it's the chi-squared test statistic, and maybe you know how to do that for measuring goodness of fit. You basically just bin everything up. You look at how many observations are in there. You take the difference of them. You square them out. You add those up. You divide by the expected number as well. So you take the expected minus the observed. We can call this the expected, that the observed. Take the difference between those, square them, divide by the expected, add them all up as you run through all these different binning scenarios, and that's supposed to have an asymptotic chi-squared distribution. There's something called the g-test that's slightly more powerful. It's also a chi-squared test statistic. It involves using a log, and that's probably why they didn't use it in the 1920s, but we probably should use it. So it's a slightly better test. So it just kind of goes to show that things that are slightly worse can linger for hundreds of years because of something was hard to do 100 years ago, but it's not hard to do now. There's also the Kolmogorov-Smirnov test. So, and somebody mentioned that last time. And that's if you look at the empirical CDF and you take the maximum difference in the empirical CDFs and you that's your test statistic. And that has a distribution in itself. And so you can study that. And in the non-parametrics class, they would teach you about that. And there's all these assumptions in the chi-squared test, in the Kolmogorov-Smirnov test, obviates a lot of those assumptions, gets rid of them. The test is slightly underpowered compared to the chi-squared test if all the assumptions hold. Things that maybe you know. I like this better. I'll take this over any sort of goodness of fit p-value based test all day long. And the reason why is my eyeball's better, or it's at least looking for the right thing, this linear pattern, where here's a fact, all of those tests, if you even just have a little tiny difference in the distributions, and you crank up n really high, that little deviation will correspond to a very small p-value. And so it could be extremely close. And so here's my conjecture. If you're testing normality or anything like that for any data set that's real, you're going to end up rejecting your assumptions if n was big. When we get around to p-values, we'll see that's a common thing. If n is big, your p-values tend to be extraordinarily small. So that's a bit of a problem. I like this. I can see that they're different. I can see that they're mostly the same. And in the tails, they're a little bit off. So see that the tail behavior is different. Again, no surprise. So Bootstrap works okay. It tends to underestimate uncertainties because usually you don't see things in the table. Okay. So they're about the same. If we crank up these numbers, let's run this one more time.
Before you do, sorry, I have a question on the QQ plot. We are looking for a linear line, right? But at the tails, we can see it's off. Can we see that it's over and underestimating by looking at the QQ? Okay.
Yeah, exactly. You can see which one is over and which one is under. So it's basically that pattern where the tails inflect in that direction. Says that the tails in the Bootstrap distribution are a little bit thinner. They don't have as much data
So
in
it's
there.
underestimated?
Yeah,
Okay.
exactly. And it depends on which one you input in there first. Let's crank up these numbers. Make this a little bit bigger, maybe 51. And maybe make the Bootstrap iterations a little bit higher. Just so that we converge on that thing. And they don't need to be the same numbers. So one more run of this. Get rid of those. So we're starting to resolve that distribution a little bit more because n is 51. And so we can see a little bit more. So ran all my Bootstrap iterations. That looks fast, and things look better. So I'd say it's more linear. So no surprise. So there's some asymptotics on n. Exactly what are they and how big do I need n to be? Go out and get more data. You can do a power analysis up front, but you need to know the distribution. And so again, this is obviating that. So it's really a difficult question to answer. What I usually will do in cases like this is I'll make sure my data is able to forecast other data in the data set. Very frequentist idea. Cross-validate. I do it all the time. I think it's a good idea. Okay, so you can kind of see this right here, that it's more linear. Question is what is this distribution? And we could try to do a test there. So if I wanted to test against normality, I could do the exact same thing where I could look at an actual normal distribution and I could compute its theoretical quantiles. That's not a simulation-based thing. And I could compare my empirical quantiles to my theoretical quantiles. And I could check that. And so the way we do that is we use QQ plots again. So QQ plot, I'll say figure 4. QQ plot. And I could look at maybe my rep stats. That's going back out into the population, that replicated distribution. Rep stat. And if I just type in QQ plot and I don't say anything about the other distribution that I'm comparing to, it will default to normal. Where's rep stat? Oh, you know what? I don't output my stuff. Let's do that again. One more time. It's not a global variable. So this is my favorite part of my job. When code's running, I feel like I'm really productive, things are happening. Okay, so maybe not as linear as last time, but I kind of liked it. Like if I saw this, I probably would, if this was a real science problem, ask, hey, what's going on there? That's really weird. You know, and I'd investigate that for a while, and I'd probably come up with, that's just a small gap in there. So it missed some data point over in one of those troughs between the three nodes. It's just an artifact. So, but pretty linear, I would say, all the way through, but there's a little offness right here, and I can tell where we are in this space where it's a little bit off. And that's what I really like about QQ plots, because it says in this part of the space, wherever that is in this three-modal distribution, I'm a little bit off right there. And that's that little chink in there. Okay, so rep stat, QQ plot. Oops, figure 4. And that's what it looks like. Right here. So here's the QQ plot of the sample data versus a standard normal. And it even goes through and it titles everything for me. So that's very nice. So I could blow those up for you and make the title a little bit bigger, but it just tells me what it is. And so it's a little bit off over on the right-hand side. If I cranked up N, we would start to see this going more and more normal. And so the asymptotics with 51 data points for a distribution that looks like the one that I've been using is not quite enough. And so I probably need that to be a little bit higher. And so if you are worried about that sort of thing and not using the normal approximation, a Bootstrap could be your friend. So we see the same exact thing, figure 4 again. Let's just QQ plot the Bootstrap for the boot stats. We see something similar. So actually that might look even a little bit more normal than my replicated stats. So why is that? It's an artifact. So this is back to Jenny's question early on. If you're bootstrapping over X bar, your distribution that you would end up getting after converged, and I might need to run it a little bit more to get it perfectly refined, or it's refined enough, it's good enough for me. I might come out and find out, oh yeah, that X bar thing, when I bootstrap over it, it's normally distributed. And so we're really reconstructing the central limit theorem. So without knowing any math. So that's kind of cool. Let's just think about this. So from our bootstrap replicates, let's give us some notation. So let the beef bootstrap rep be just this thing, xb1, xb2, out to xbn. So that's my beef bootstrap replicate. I'll call it xb is equal to that. And so if I wanted to compute my test statistic, x bar B would just be sum of the xbi's, I goes from 1 to n, divided by n. So that's my estimate from my B bootstrap replicate. So at the end of the day, I get this whole distribution. And maybe I want to know what the mean of that distribution is. And so I could end up looking at my bootstrap distribution and compute my total mean from that distribution. So if I ended up looking at xb bar, this is a number. I sum this over b, goes from 1 to cap b, and I divide by b. So this is the mean of the bootstrap distribution. Is this thing, what does this go to? Is b goes to infinity. I did this over and over and over again. It goes to x bar. So what am I doing? What are all these things? They're averages. So this is an average of an average. And if I'm sampling uniformly from that distribution, I'm getting everything with the original frequency that it's represented in my original distribution. So if I just did it once or twice, we might have something really weird just by chance. Maybe you got the first observation all n times. Gotta be spooky, but it could happen. Just as likely as anything else. So this thing right here is going to go to x bar, which is just the sum of the xi's divided by n. You can convince yourself of that. So the bootstrap does not give you a better estimate. And so this might be, at the end of the day, the estimate that we're going to report but I could have just reported this in the first place. So what you're getting out of the Bootstrap is that distribution so that you can quantify uncertainties. That's what it gives you. For X bar, it's not that useful unless n was like really small or something like that. So that the central limit theorem didn't kick in, but then I'd be worried that I didn't have enough samples for my Bootstrap rep. So probably don't want to do anything in that case. And so where you can really use this is in some more devious distribution, strange distributions. So instead of the mean of X, maybe I take the mean of, I don't know, I could do some other test statistic. Let's just look at the variance for a second. So maybe you don't know what the distribution of the variance is. You might actually know. Probably some sort of a chi-squared distribution. Asymptotically. So I could just change that statistic and rerun everything. I just go back out, compute those 500 samples going back out into my population. I get everything at the end of the day. It looks like the distributions are about the same, the Bootstrap distribution and the replicated distribution. That's what they look like. They're a little bit off from each other. We can even look at the QQ plot and see they're really off over in the left tail. But the nice thing is I don't have to do any math. So what's the distribution of the variance of this data? It's this, approximately. And so it's a nice approximate tool. Computational in nature, so 100 years ago you couldn't do this. But nowadays we can take it for granted. You can probably do it on your watch. Okay, I think that's it. Any other questions about this? So read up on that if you'd like to read more mathematical details, but I'm going to have you play around with it. At the end of the day, we're given a particular n, you know, and so it's only going to work so well, and it's going to depend on the problem at hand. So I'm going to have you apply this to Bernoulli data and try to estimate some function from that that is a little bit tricky to estimate. And we'll see how well the Bootstrap works. The Bootstrap can fail. Bayesian methods can fail, asymptotic methods can fail, everything can fail in its own way. And so we'll try to get an understanding of when techniques fail in here as well. I think right now we've shown it's actually working pretty well, surprisingly well. Okay, let's jump into order stats. So let me tell you what they are first. By the end of this sequence of lectures, if somebody says, I want the joint distribution of 12 different order stats, you'll be able to derive that and write down the formula for them, no problem. So if you read through the book and get a description of those formulas and their derivation before Monday, the way that I'll present it to you is a lot easier to remember. But it might be helpful for you to read through the book and see their explanation. I remember feeling a little bit confused when I first read it, and I remember thinking, I can never remember these formulas. So I need to write pictures. So I'll try to draw you a sequence of pictures. So order stats. So let me just start with a question. Say we have some distribution. I'm going to call this. I kind of like to start with examples first. So I'm the anti-mathematician. Let's just see some examples, and then we'll go and we'll prove everything. So f of x, 1 over 2 to the x, where x goes from 0 to 2. So this is a density function right here. Let me just ask you a question. What distribution is this?
No, uniform.
I hear that all the time. It's not uniform. I don't know what it is. So a uniform distribution isn't that. This density function looks like this. So it's not uniform, it's something else. So over to the right-hand side, I start to see more and more mass, so I'm more likely to sample these things. I don't know what the distribution is, I just made it up. So let's say we get Xi's from this, say they're IID. Everything I'm going to tell you about for this requires everything to be IID. And let's just ask a question. So let me just give you some notation. So X1 is going to be our min from all of our data points. So cap X, where cap X is going to be X1, X2, X3, X4, X5, X6. So I'll say n is equal to 6 for my example. And so I see 6 values over here. 1, 2, 3, 4, 5, 6. That's probably not a representative sample. So, but I know I'm going to see more things over here, at least I expect to. So those are my 6 things. 1, 2, 3, 4, 5, 6. And let's just ask the question, the 5th biggest thing, which is this one right here, and I don't know which order I got these in. This might have been the first thing, this might have been the second thing, this might have been the third thing. But then I'm going to order them all, and this one right here is going to be X1. This will be X2, my second biggest thing, and this will be X6. All the way over here. So X2, second largest. X5 with the braces, it's going to be my 5th largest. In X6, because n is equal to 6, this is my max. So I'll just write it out like that. So this is X5, right here, and there's my max. So let me just ask a question. We'll see if we can do this mathematically next time, and I'll try to give you the right argument. But let's say we want to know what's the probability that X5 is less than or equal to 1. So we might want to compute that. And so what I need is I need the distribution for X5. Yes, please.
It's second largest or second smallest? X2.
Second smallest, thank you. Obviously, by the snicker, they're like, all of you wanted to ask that question. So just throw it out there, if you know what I mean. So I do this all the time, apologies for that.
But
So, yeah,
isn't
second.
X5 the second largest? And then,
5th smallest. That's what I mean. So my signs go really berserk at 9 o'clock in the morning. So we've got at least the easy part out of the way. I'll try to get the rest right. So I'm instilling confidence, I can tell. So my question might be this. So what is this? How do you compute it? And so that's an interesting question. And we'll figure out how to do this next time with a combinatorial argument. But what I really mean is, if I went back out into this distribution, over and over again, I sampled 6 things, and I looked at where the 5th smallest thing is. So X5 with the brace, the 5th order step, it's going to vary, and it's going to vary somewhere around here. So it's going to be jumping around. And I could build up that distribution. And so that's what this question asks, is what's the probability that that thing is less than 1? The 1 is here. So it's probably pretty small. And I've simulated this for us, so we can look at that. So I wrote a piece of code that ends up sampling from this distribution right here. So there's my line of code that does this. And I'll share this with you. I can put it on Slack or the webpage, so look in both places at the end of the day. And so this is my sample from this distribution. X divided by 2, X lives between 0 and 2. So what I've done is I've generated a uniform random number. I've done n of them so that I can do this. So n right here, let's just say n is my input, J of my order statistic, so I can modify this a little bit. So N would be 6 in this case, and J would be 5 to answer this question. So I could input N, generate some uniform random numbers, multiply it by 4, take the square root, and that's a draw from this distribution. Does anybody know what I just did? Why this works? This is called inverse CDF sampling. So in the homework, you'll have a problem to play around with this. And I can show you how this works later on. So I took the CDF, I inverted it, and that's what it is. So this is a draw from that distribution. I'm going to do it, get 6 different draws. I'm going to sort everything, get my jth biggest one. I'm going to hold that. I'm going to do it over and over and over again and reconstruct that distribution. So let's just look at what that distribution looks like. So I've already inputted my numbers 6 and 5. To match this question, this is the distribution of the 5th order statistic right here. So it's stacked against 2, and the probability that it's less than 1 is pretty small. And that's our number, at least our simulation of that. So what we want to come back next time is figure out how to do this mathematically. So what we're going to do is we're going to figure out what the distribution of x5 is, or xj in general, and then I'm going to show you how to work through the density of that distribution as well. And they're both relatively easy if you can remember the right picture. I'll show that to you on Monday. Have a great weekend, you guys. Bundle up, stay safe, don't drive.
Maybe. Probably.